Hi class, so today what we're going to do is use trig identities to actually help us perform and compute integrals. So this section is called Trigonometric integrals, and what we're really getting to do is leverage trig identities to make integrals easier, or in many cases, actually even possible to compute. So we're going to be able to compute some antiderivatives that we otherwise would not be able to compute unless we use trig identities. So a lot of what we're going to do today is try to pair different identities with sort of what we see in the integrand of many integrals to see if we pick up on some patterns and that type of idea. The other thing I want to point out is between this type of trig integrals we're going to do where we're just blatantly substituting identities into integrals, the substitutions are going to be different than what we did for u-Substitution. The big thing here is we're not going to be changing the variable that we're integrating with respect to, unlike u-Substitution when we put things in terms of u. So we actually don't have to change our dx into anything else. So without further ado, I just want to give an example of some of these integrals that we might see pop up. So for example, here are two integrals. And both of these integrals would be very difficult to perform unless we had trig identities at our disposal. So in the first case, for example, I just want to point out a couple things. So if we're looking at this top integral, what makes this integral difficult is the fact that both of these cosines have different arguments. So in the case, we have a 5x, we have a 2x, so we can't actually just use any types of cosine antiderivatives we know as it stands right now. Down below in the second integral, what makes this particularly difficult is the fact that we have a sine squared. We know how to integrate just a sine by itself, but a sine squared is a bit more tricky. So what we're going to do to give you a flavor of this is look at what trig identities we have at our disposal. So for example, let's go back and just look at the first integral up top. Now, just glancing at all the variety of identities we could use, what we want to do is try to pair the identity with what we see sitting there in the integrand. Namely, in the integrand, we see a cosine 5x, cosine 2x. So we sort of see this a cosine of A times cosine of B situation that's getting reflective of this identity. So I'll just say here, what might be useful is the identity of cosine A times cosine B equals 1/2 of cosine A minus B plus cosine of A plus B. And we'll actually use that substitution next. Let me just move this over a bit. For the bottom integral now, if we're just thinking about, well, what identities might be useful? We have a sine squared kind of sitting there in the integrand. So we're asking ourselves, what identities do we see sine squareds in? Well, we see a sine squared in this top identity, sine squared plus cosine squared equals 1, one of these so-called Pythagorean identities. But it looks like if we solve for sine squared, we're going to get a cosine squared, which just gives us a cosine squared instead of a sine squared. We still don't know how to integrate that cosine squared. So kind of looking down our list, we can see where other sine squared aspects come up. We see a sine squared somewhat coming up in this cosine double angle identity. We also see a sine squared in this bottom half angle identity. And now I would argue we can use either this double angle or half angle identity, because actually if we go ahead and solve for the sine squared in this double angle identity, we will actually just get the half angle identity down here. So what looks like it might be useful in this case is this identity that sine squared of x equals 1/2 times the quantity 1 minus cosine of 2x. And now, without getting into why it looks useful, it looks as though, well, what we traded was that squared term for a power of cosine to the first. And we know how to integrate cosines to the first power, so this looks like it might be a fruitful substitution. In the next video, we'll go through why.